papers this morning. The first one is using clusters of concepts to extract semantic relations from standalone documents, from João Ventura and Joaquim Silva. We have 25 minutes to the presentation and then 5 minutes for questions. And I'm going to give you a sign when there's 2 minutes left. Okay, so please start.
Oh, okay, it's good. My name is João Ventura and I'm presenting this paper. It's about the extraction of semantic relations from what we call standalone documents, and I'll show what standalone document is. So first of all, I don't know in what areas you people work, but as you may know, or some of you may know, semantic relations or the extraction or the usage of semantic relations have been applied in lots of things, like word sense disambiguation, for instance, to understand the intended meaning of some words or sequence of words or a concept. Also for query expansion, it's also an application of semantic relations. For instance, where we want to select candidate terms from lexicons, like WordNet. There will be a presentation on a Portuguese WordNet. And also for the extraction of implicit keywords, it will be not the following, but the other one, a presentation about the extraction of implicit keywords. So about the current work, or about works or approaches for the extraction of semantic relations. Usually there are the statistical and the non-statistical. I separate this because I work with statistical. So the problem with non-statistical approaches, it's because most non-statistical approaches tend to be dependent on something, or language or structure. Okay, so I give some examples. Where, for instance, I point the last one, where some approaches tend to use external semantical lexicons like WordNet. So there's always a kind of a dependence on something. So on this work, we want to use the statistical approaches, but statistical approaches also has some problems. Because, as you may know, statistical tends to use large collection of data. In this case, if you want to extract semantic relations using statistics, we have to use large collections of documents. And one idea of the statistical approach to the extraction of semantic relations is this idea: if a pair is related throughout the same documents on a collection of documents, they are somehow related. But unfortunately, this has a problem for the specific thing, which is the standalone documents or small collection of documents. The problem is because these standalone documents are usually not small text, but documents of unique subjects, technical reports, or just single documents. So in this case, sometimes we don't have external lexicons, okay, because the subjects or the domains of these technical reports tend to be too specific, and no one has ever done a lexicon, a WordNet, or a dictionary talking about those very specific subjects. And because they are small or small collections of documents or unique documents, we don't have enough statistical data. So to solve this problem, we have to use these things we've called clusters of concepts. The idea is very simple, very simple. So for instance, take this small, you don't need to read it, but just see it. This small excerpt from the arthritis Wikipedia document about 2 months ago or something like that. as you can see, this document or this small excerpt, which is a paragraph, talks about lots of things, but there are two important concepts being talked here, which is gut and uric acid. And as you can see, I've put it in on black, bold. As you can see, gut and uric acid occurs a lot on this paragraph. So the idea is that this gut, as it occurs a lot on this area, on this paragraph, tends to do what we call a cluster, so an high density area of occurrence. And also uric acid. So our idea is very simple. If the concepts form clusters in some areas and the clusters intersect, so somehow they are related, or we say that they are related. So first of all, how do we find clusters? So a very simple thing. We have a list of the positions where a concept occurs on the document. Okay, it occurs in position 20, position 60, whatever. And then we do a simple mathematics. We compute the average separation. The average separation is just if the concept would occur randomly, how would it be? How would it occur throughout the test? So it would occur uniformly. Okay. So the idea is that if the distance or the successive distances of occurrences are less than this average separation, so it means that they are closer than what would be expected by if they were random. So the idea is that if the occurrences tend to be very close to each other, so the concept makes a cluster in that area. But this has a problem. We have identified the problem with this, is that these tend to favor rare concepts. For instance, a little example. So imagine that we have a document with 2,000 words, a regular Wikipedia document, and a concept occurs only 4 times. If it would occur with a separation of 400 words, okay, 400 words is less than 500, that would be the result of that equation. That equation would give 500, and if the separation was 400, our algorithm or our idea would say that, oh, there's a cluster there. But 400 is a lot of distance between 2 occurrences of a concept. The meaning of that concept would get lost on the conversation on the document. So that has a problem. Another problem is that idea or that equation also tends to harm frequent concepts. Okay, I will talk a little bit more about this. So we have made some observations. These graphics here, it's on the left, it's for English. As you can see, that on the x-axis is the number of words. This is the number of words in paragraphs, and on the y-axis is the number of paragraphs. So as you may see, there's a peak on 50. It means that most paragraphs on English documents have 50 words. And then it starts to drop, and you have to believe me, but there's 90% of the paragraphs on English corpora, on English documents, have less than 150 words. And this also occurs for Portuguese and for German, which were the languages we also tested. So on the right, that graphic shows the average number of words by document or by size of the document. The idea is very simple, is that independently of the size of the document, the average number of words on a paragraph is somehow static. It doesn't change a lot. So with that, we have rewritten our idea we have rewritten our equation to make that threshold. So the idea is this: if the separation between two successive occurrences of a concept is bigger than 150, it doesn't make part of a cluster. Less than 50, it always is part of a cluster. Okay, and we do between those numbers we do the previous equation. we have written this. I won't explain this. We have written this on the paper. A concept. The problem is that on a document, a concept may form clusters on several spots. For instance, on the arthritis document, a good, since it's only one type of arthritis, it only occurs on one area, so it makes only a cluster. But arthritis, the word arthritis, which occurs a lot on the document, makes lots of clusters on the document. And we also have a thing on the right side, an equation which we call cohesion. The cohesion is just a measure to say how much cohesive a cluster is. If a cluster is very if the words on the cluster, or the concepts, the occurrences of the concept in a cluster is very separated, the cohesion is less. If it's more near each other, the cohesion is bigger. Sorry, something. So the idea is, since we have a way to find where are our clusters, okay? So we have a cluster. Imagine we have a concept A, which could be good in that example, and the cluster B, which was uric acid in that example. We want to measure if they intersect with each other, or if they tend to occur on the same paragraph. So we have this equation which just measures how much of one concept, or the cluster of one concept, is inside the cluster of the other concept. So finally, we measure. It is important because we don't find semantic relations, or better, we don't know how is the semantic relation between two words. We only measure how much they are related. So we don't know what type of relation that is. This is important. So we use that equation up there, which is, if we have a concept A, a concept B, okay, just the average intersection. We want to know how much they intersect and how much cohesive each concept is. So we just multiply all these things and we have our values. I'll give here on this table an example. So this is for the arthritis article from English Wikipedia. And as you can see, good is related, the best relation is good with good arthritis. It's the same thing, it's like a synonym. But also good is highly related with uric acid. It's not a synonym, so that's what I said. We don't know the type of relation, we just know how much related they are. And then, as you can see on the bottom, systemic history, they are not related at all. This has a small thing that you should notice. For instance, almost the last one, the previous one, rheumatoid arthritis, psoriatic arthritis, you could say, oh, they are related. But the problem is, on the document, they are not related at all, because rheumatoid arthritis is one type of problem, and psoriatic arthritis is another type. One is on the beginning of the document, the other is on the end. There's no explicit relation on the document. Also, we have also tested this our approach for Portuguese and German. Okay, they all have also, believe me, they have good results. The German also, I don't understand much of German, but they are good. Some results. Okay, so we have made an experimental thing. We have tried our method with some Wikipedia documents. They are here for English, Portuguese, and German. 10 documents of each language with more than 2,000 words, and we have extracted 30 pairs of concepts from each document. I've not written here, but we have used an automatic concept extraction, which was a work from last year, our work from last year. So the idea or the criteria we used for the classification was just this. A pair of concepts is related if they are explicit on the text. Just to remind you that psoriatic arthritis and rheumatoid arthritis, although the classifier could say, no, they are related because they are both types of arthritis, but they are different types of arthritis, so they had access to the document. So as you can see, we have good results for precision and recall. 90% precision, 85s, 80s for recall. So this was our result, and we have also made a small test for collections of documents, just to see if we could use also this idea of clusters of concepts to help on the extraction of semantic relations from big corpus. And so I'll give just these two tables to see. So the first table is the correlation values. We have used a metric similar to Pearson's. These are the correlation values for concepts co-occurring with good. Okay, and as you can see, the biggest or the highest values are names of persons. This is because the correlation, I will remind you, the correlation says something like this: if two concepts tend to occur on the same documents, they are related. So the problem is that there was a document talking about goods and relating it with some person. I don't know what the document was, but it was some person, and that I think was that Lawrence something, and there was this Dr. Johnson. We treated him with the goods, something like that. So because it was only one document, the correlation between goods and these names was very high. But the problem is, for some applications, information retrieval or thesauri, construction of thesauri, we may want to rank the values in other way, or to put the best concepts or the best semantic relations on top. So our idea was just a simple thing. So we have the correlation on the bottom table. We have the correlation. On the left, we have the semantic, the clusters, semantic clusters on the middle. So we just did an average between those values. And as you can see, doing just this simple thing, an average between a generic analysis of the entire corpus, the correlation, and then an analysis to a document, on the document. So as would be expected, the Goodyear treatise occurs better with good than names of persons. This is to say, just because the names of the persons on the document, which talks about someone who had good, the names of persons are not related explicit on the text. So we have better results for better, what we say, it's better keywords or better concepts, and the names of the persons, they have lower results. Okay, so thank you very much. I hope it was simple. They have a problem. They use only words, single words, related semantics. Let's say that the normal distribution is the baseline. We compare if the clusters are, we say that the clusters are intersected if they sorry, you're talking normal, not uniform. Sorry. Okay, what you want to know about normal? We use normal distribution. We don't use any distribution at all. This is small document, small collection. Statistics doesn't work a lot on the yeah, we say it's statistical because we use mathematics. We count numbers. We say that is statistics, our approach. What do you want to? Define what you want to know about parametric? We don't care about we have simple texts from web, something. We don't do any kind of analysis. This is a raw approach. Okay. Hmm. Oh, okay. Okay, maybe for us it is not important at all. We have a text, we want to extract semantic relations from text. We don't care if it's normal, weird, we don't care about that. We have a text, small text, 2,000 words. How do you know that? You have tested this? Hmm. But for instance, are the texts on the Wikipedia normal or not normal? So it's not important, but you're keeping saying that. Okay, okay, okay. Okay, this is more. This is better explained on the paper. I won't quote what I say on the paper, but the idea is there are some approaches like they tend, for instance, something and something, things like that, where there's a pattern specific to a language, or for instance, there are some approaches to say this, comma, and this and this. If this type of words are written like as I'm saying are written on the text, they extract. They say, okay, so this A and B and C, these A, B, and C are related.
It's not related to pattern recognition approaches. Okay.
It's not. So it's related with that. Semantic lexicons.
No, I mean pattern recognition.
You're talking about. We also use our name clusters, and people thought that clusters.
Because
we talk about clusters.
No, pattern recognition.
Words. We are talking about something that people think that we're talking about other things.
No, you mean a language-dependent approach are mostly like poise approaches.
Part of speech.
Yeah.
Yeah.
But pattern recognition approaches are not language-dependent. LSI is language-dependent? No. And it's part of pattern recognition approaches.
Oh, so no. So this time, okay. Patterns on languages. Is that it's that what I'm talking about? Patterns on languages. Okay, maybe the word recognition is not the most appropriate one, but it's patterns on patterns like English patterns. This and this and this. These words on the documents.
And as a final comment. RapidMiner has a text mining plugin that do the same thing, and
they do clusters on RapidMiner.
No, not clustering, but the captures the relationship between the boards, and
on small documents. Small documents.
Yeah. And for data evaluation, you computed some precision and recall. I could not understand. What was your data and what labels you had in this data? Precision recall.
We have these documents here.
So you manually evaluated?
30 concepts, it's not too much.
Okay.
I say that, 30 pairs of concepts. Just to say, okay, this pair is related on the text, yes, no. Simple as it.
Any more questions?
I'm sorry, but I still didn't get this part of the evaluation. Okay. How were the pairs formed? How did you select them? And how was the evaluation actually? Can you be more precise?
Randomly extracted. We have a work from last year, which is concept extractor. I will talk a little bit more on the next presentation about it. So we have this thing called the concept extractor, which extracts concepts from documents. We have run it through each one of these documents, extract concepts, and then 30 random concepts from each document.
Yes,
So that was how we extracted 30. And then these 30 pairs, okay, I understand. I think I understand it out. We didn't compare each one with each one. It was not there. It's what 30 pairs. So for each pair, we just computed the relation. So for each document, we had 30 semantic relations, which were to be classified.
And you labeled each pair
as yes or no, related or not. Yeah, we just have a very simple thing, a text file with an X if they are related on front of it.
And are 30 pairs enough to...
For each document, yes, 300, 600, 900.
Okay.
I think 900 is a lot.
And it was correct if you would label it as correct?
If the classifier saw that the relation was explicit on the text.
No, when example. In your gold collection or in your golden data.
Good is related with uric acid. You just have to read it. Okay, good is caused by the position of uric acid. It's related.
So the evaluator that was creating would have to read and
yeah. The access to the documents was guaranteed.
Okay. And also following the previous questions, I might have missed something, but I also don't get the real differences between this approach and, for instance, PMI information retrieval, PMI-IR from attorney or PMI, pointwise mutual information.
Pointwise mutual information.
Yes. And others, and LSA, and also the approach of Lean, very old approach.
Will this answer to your question?
Okay, that's sufficient statistical data.
I think it probably will answer.
It will probably answer to some. Okay.
See this problem here. You have this small paragraph. You have only 1, 2, 3, 4, 5 occurrences of good and 4 occurrences of uric acid. Okay.
But if you just have this, you cannot have very strong conclusions. You don't have enough data, so you cannot. Okay, you can conclude something from this small piece of text, but you cannot.
We can conclude this
from that small piece of text, but
yep.
Okay. Well, it might be useful for something.
Yeah, it might be useful for this. Okay, we have an eye, and we see the collection, and then for each document we see if that pair is related also on a document.
In a new document.
Okay, so I'll talk. I think I've already passed my time. No? It's 30 minutes. Okay, sorry. So, as you can see, if you on the first table, we only did the correlation. Okay, it's like pointwise. Think about pointwise, but correlation. It's
okay.
We use another metric. Yes, same thing. Okay, on a corpus, lots of documents. This corpus had 4,000 documents. So we could say that Lawrence McHenry is related with good. Okay, Dr. Johnson is related with good. Esther Trail is related with good. But why do we want to know that? That hasn't any usefulness. So we go to the document level and we can say this. That good is related with gouty arthritis on the document. On the document arthritis, good is related with gouty arthritis. Good is related with uric acid. Okay? So when we go down again to this example, I say that, okay, good is related with gouty arthritis. So we do an average somehow. This is just a small example, just to say how useful this can be. So we just do an average, and now the names that on the correlation were pretty high classified, doing an average with the correlation and the analysis on the document level, we now push the names down. Did I?
Yeah, but you needed the big corpus anyway.
No, this is just to say that if we have a big corpus, we can tweak these things to be a little bit more useful. This is an example. We don't need a big corpus. We just need one paragraph.
If you have a big corpus, you would probably use other approaches. Out, I think.
Well, no, we use the correlation.
Okay. And have you compared your results with those other measures just to make sure that your approach is better in this?
We couldn't
specific
find. Okay, you said about latent semantics. I'm not completely sure. Sorry, I'm not completely sure that latent semantics would solve this small text, and we couldn't find any other statistical ways of solving this. We wouldn't make the non-statistical approaches. Because of this non-sufficient statistical data. But we can have this...
Yes.
No, I don't know. I'm not. I don't share. I didn't say I'm not. I'm not completely sure you can do this.
No, but you could be. Yes.
Yeah. But I wasn't aware that latent semantic could even solve these specific types of problems. Okay.
Yeah.
So maybe I think we reached the
the
end.
Okay.
Thank you, João, again. Then we'll move to the second paper, Density-Based Graph Model for Multi-Document Summarization by Mohamed Reza Validezadeh and Pavel Brazil. Sorry about if I mispronounce it.
Hello everyone. Our paper is about density-based graph model for multi-document summarization. I will talk about introduction and previous works. After that, I will discuss about our idea, that is density-based summarization, and we will show that our idea reduce number of iteration for the summarization, and the final we will show experiment results and the conclusion. So what is the summarization? Summarization means generate a short text for single or multiple document. There are two main methods. for summarization. One is extractive and the other is extractive method. In extractive method, system tries to concatenate only important sentence into the summary, and in the abstractive method, system tries to reformulate or retelling the original text with the help of natural language processing in the summary. There are some techniques for this area. One of this graph-based model that's used widely in the extractive summarization. Summarization has some steps for the graph-based model. The first step is pre-processing. It means that sentence splitting, stemming, and stop word dropping. The next step is graph generation. It means that nodes are sentences, and the similarity between the sentence are links between the nodes. After that, we must apply a ranking algorithm to the graph. For example, LexRank for generic summarization and TLexRank for query-based summarization, we can say. And the final steps is select important sentence based on their score, and concatenate these sentences into the summary. One of the most popular graph-based algorithms, it means ranking algorithm, for generic summarization is LexRank, and for query-based summarization is TLexRank, and they are based on PageRank. As you know, PageRank is an algorithm to give the score to the nodes in the graph. If one node has more important neighbors, it gets higher score. But when we generate a graph, some information will be omitted. For example, which sentence is related, which document, or how many sentences there are in one document. So we want to solve this problem in the summarization. Erkan in 2004 proposed LexRank based the PageRank. The first equation is PageRank that try to give a score to the nodes. Here nodes is sentence in the graph, and LexRank is one adapted from the PageRank. As you can see, they try to use similarity between the sentence. For example, similarity SI and SJ. SI and SJ is two sentences that are two nodes in the graph. They use this similarity to adjust the PageRank and use in the summarization. The other researchers try to propose some ranking algorithm. For example, as I said, LexRank for generic summarization and TLexRank by Ottobacher for query-based summarization. Means query-based is you have one document or one collection, and you give one query or one short document, and based on this you want to give the summary of the collection. And Foraway try to add concept of document and query to the LexRank and TLexRank. As you can see in the LexRank equation, you just try to give a score to the sentences, but just by similarity between the sentence. It's not you cannot see SI or SJ related to which document. You have one collection. This collection has some document, and each document has some sentence, and this SI is related to one of them. So you can, this equation cannot show SI related to which document. And Foraway try to solve this problem. And we want to use one concept. Its name is density. What is the density? Density of document try to expresses how much its elements or each sentences are close to each other. We believe that if the sentences of one document are close to each other, it means the document talk about a specific issue, and the sentence of this document is more important to the summary. The easiest way to compute the density is inverse of the radius. We can compute the centroid of the document, and based on this, we can compute the distance between the centroid and each sentence. This radius we can use as a density of the one sentence, and for the document is average of these radiuses. Radu in 2004 proposed centroid-based summarization. In this paper, we show that centroid-based summarization is different with the density-based, because they use the centroid value. It means the sum of the centroid value of all documents for one sentence to compute the centroid, and it is different with the radius. And if we had time, we can show at the index. For adapted centroid value, use centroid value at the Lex rank for generic summarization. For example, this equation without these two terms is Lex rank, and Foraway added the concept of the centroid value and the similarity between the documents that these sentences are related to them, and show that this adapted Lex rank, that is for generic summarization, is better than Lex rank, and they call this DSRG. We try to use density based and change the ranking algorithm and use the inverse of radius for the Lex rank, and adapted the Lex rank like this, and the results show that this is better than Lex rank, and the adapted Lex rank that Foraway proposed that. For generic is like this. Ottobacher adapted Lex rank to query-based summarization, and they call this T-Lex rank. T-Lex rank is for query-based summarization, and they added this term, similarity between the sentence and the query, to compute the score of the sentences. And we, excuse me, and Foraway added the concept of the which sentence belong to which document. It means the similarity between the documents add to the T-Lex rank, this term, and they show that this ranking algorithm work better than T-Lex rank. And we adapted T-Lex rank by added concept of density that's computed by radius. As you can see, we add radius. If SI is near to the centroid, it means that this sentence is more important, so we must give more score to this sentence. Experiments show that our algorithm is better than the other at the runtime. We know that runtime is very important for all algorithms, and the T-Lex rank, page rank, all are iterative, so they are time consuming. And our algorithm take less number of iteration to converge. We do our experiments on DOC 2004 for generic summarization, and on DOC 2006 for query-based summarization, and we used Roach toolkit to compare our results. This table shows that our algorithm for generic summarization is better than LexRank and four-way adapted algorithm that is DSRG, and we improved for generic summarization at least 2.6% than the others. And for query-based summarization is like this. As you can see, our algorithm is better than the others. At least we improve 2% in Roach 1 or 2 and SU4. And this graph shows that our algorithm for generic summarization gets less than number of iteration from the others. For example, here we get about 20 iteration, and the other 30 or 50 iteration they need to converge. And for query-based summarization is like this. We need less iteration than two other algorithms. At the final, we proposed the concept of density to the summarization in the field of a graph-based model. We compare our algorithm with the final algorithms that are in this literature. The Roach toolkit shows that our algorithm is better than the others. And for the next our works, we try to use some information or method to try reduce more number of iteration and generate faster summary for the collection. Thank you for your attention, and I'm here for your question. Yes.
This summarization system, is it working for the English language, I think? Yes? Yes. Just for English?
Excuse me. Because the collection for the test is doc, and doc are collected from some journals, and all of them is in English.
What would be the changes if you wanted to use for any other language?
The method is, I think, language independent, because we split the sentences.
But what are you using for splitting the sentence? You need a pause. You need a parser, I think. Yes?
Yes, we have, for example, Doc 2004. It is one collection, for example, 50 document, and you need the 50 collection, each one. For 2004, I think 25 document. You have 25 document, and you need to summarize this 25 document to one document, and its length, for example, for 2004 is 335 byte, and for 2006 you must generate one summary with length 250 words, not more than. You have, for example, 25 documents. You want to summarize this collection to one summary.
Yes, but if you wanted to use for Portuguese, for example,
yes,
you would have to have a grammar for Portuguese.
The other researchers tested, for example, LexRank or T-LexRank for multi-language. Okay. They tested that if it's worked for example, English, it's worked for other language.
Thank you.
You're welcome. Any more questions? Oh. Thank you. Thank you.
With the third paper, automatic extraction of explicit and implicit keywords to build document descriptors, by João Ventura and Joaquim Silva.
So, this time our work is about the extraction of explicit and implicit keywords from documents. So, as you may know, I like to control time. As you may know, keywords are single words or multi-words which describe somehow or somewhat the main topics of the documents. And our hypothesis, this is because I'm doing my PhD thesis, it's that keywords are the most informative concepts on documents. Again, the word concepts. Okay, so as you may know also, keywords are useful in many things, like information retrieval. It's main use. So document classification, document clustering, search engines. A little bit about related work, and this is a characteristic of our work. We tend to use, okay, some may say it's not statistic, but this time it's more statistic, we use math, okay. So there are linguistic approaches. But the problem with linguistic approaches, they use language-specific tools. Part of speech taggers, patterns, syntactic patterns. It was also the answer to the question on pattern recognition, but pattern-based, so syntactic patterns, stemmer stop words list. Okay, we don't use that. We don't want to use that. We want to have a text, any language at all. I'll continue. So, structure-based approaches also. So they have structure dependence. Okay, for instance, some approaches use some properties like on Wikipedia documents. There are these in links, out links, those kind of things, and there are approaches which use those properties that someone already did. And there are some statistical approaches. There are also other types of approaches, but these are the main. And statistical approaches, there is, for instance, this local max, which only works for multi-words. There is TF-IDF, which is it's very known, but it has a problem with multi-words. I will show you. And there are also approaches which use the idea of a medium length of words, or median length of words. Okay, but this, what about documents about otorhinolaryngology, things like that? It fails for this. And there are other approaches which use or solves the problem for single words using like filters, okay, to solve the problem of not having a function or stop words. Okay, the problem of stop words is stop words usually are small, and to get rid of stop words, they use 6-character filters. But imagine a document talking about computer memories. Okay, so RAM, ROM, it would be discarded by these systems. Okay. So our approach, how does our approach work? So first of all, we extract concepts from a document. Our hypothesis is that the keywords are the best, okay, the best quoted, the best concept. So we use the concept extractor, our previous work of us. Then we extract the explicit keywords. So concepts occurring explicit on the text, we call them the explicit keywords. Then we extract the implicit keywords. So basically, the implicit keywords, it's like we are augmenting the description of the document. The idea, the implicit keywords are concepts which do not, although they do not occur on a document, they are somehow related to the the contents of the document. So, for instance, imagine that a document about air pollution, or a document about air pollution, maybe, or car emissions and acid rain, can be related with the document talking about air pollution, although car emissions and acid rain may not occur explicitly on that document. Explicitly, it means that it doesn't occur on the document. Oh, sorry, concept extractor. So, the concept extractor is a previous work of us, published last year. In the idea of the concept extractor is to explore what we call the specificity of a concept. The specificity is somehow, it's not entirely, it's somehow related with the number of concepts a concept relates with. So the idea is that a concept or a word, ignore concept for now, but a word or a sequence of words, if it relates on a specific type of relation that I don't talk here, but talk on that work we presented last year, the idea is if a word or multi-word tends to relate with a lot of other words, it's very promiscuous, okay? So it has a low specificity. If it relates only with some words, for instance, jet engine, jet aircraft, it relates with only these types of words, aircrafts, things like that. It's more specific. So the idea is that we have a threshold where below a specific threshold, the word or the multi-word is so generic that it isn't a concept. We don't consider it a concept. Above that threshold, or more specific that threshold, we consider that a concept. But that problem, or the work that we did last year as a problem, it has a small or a little bit lower precision recall for multi-words because of this problem. Compound concepts, or concepts formed by multi-words, they usually, or I say usually because I don't like to say never, but I don't know a case where a compound concept doesn't end or start with another concept. So as you can see in this table, the first three are concepts. They start or end with other concepts, and the last four, because they start or end with function words, they are not concepts, or they could be part of a concept, but only that multi-word is not a concept. So we want to improve this. So the idea for this improvement is just this simple thing. So we had already this spec M, which is the specification, how we compute the specification of a multi-word. I won't talk what we do here, but after we just multiply by the minimum specification of the first word or the last word. The idea is that words or concepts like the first one, since president and republic are highly specific, the minimum of president of a republic, the minimum value is very high, so it won't be too punished. Words like sequences of words like by the government, since by is a word which won't be much specific, so the minimum will push all the specification of that by the government, it will push it lower. So to say this, as you can see, we have here precisions and recall for the previous work, or for the spec M, and then for this spec M2 with just the multiplication by the minimum. And as you can see, for English, we have tested for much languages, for English, Portuguese, and German. As you can see, just for instance, for English, we have improved from 87% precision and 89% recall to 93, 95. Okay, and also the thresholds, the threshold results, they change. So we had a new frontier for multi-words, but this is not important for this work. Okay, so about the explicit descriptor. So the previous thing was just a small improvement for the extraction of concepts and for you to know how do we extract them. So the explicit descriptor, as I say, the explicit descriptor is just a list of keywords of, I think it's 10 single words and 10 multi-words, of the most descriptive concepts occurring on the text. So we just use TF-IDF to solve that problem. So we extract concepts, we apply TF-IDF to the extracted concepts, and we have results like this. So in this table, as you can see, this is for the Brain English document from Wikipedia, and TF-IDF on the concepts, and this is, I'll say this again later, but TF-IDF says that, okay, this document talks about brain, neurons, disease, animals, etc., and also talks about spinal cord, cerebral cortex, artificial intelligence, and so on. So we have, just to see the results of the explicit, we have used a Wikipedia-based corpus, Wikipedia-based corpus for 3 languages. There are the statistics of each language. And we have, again, extracted 10 documents of each language. And for single words, this is very important to say that results of applying TF-IDF only to the concepts, it's the same thing as applying TF-IDF. I will say this again. For one document, applying TF-IDF to only the concepts on the document is the same thing as applying TF-IDF to all the words on the document. As you can see, it's almost the same thing. The precision and recall are 89%, 80%, something like that. But the main difference is that TF-IDF is not good at all, or TF-IDF applied to all sequences, all possible sequences of words on the document, it has low values, as you can see here, low values of precision and recall. So if we apply TF-IDF only to the concepts, extracted concepts, in this case for multi-words, as you can see, results of precision and recall, they improve. Basically, what we are doing, we are just somehow, for the explicit descriptor, we are reducing the search space and giving it to TF-IDF. So the magic, let's put it this way, on the explicit descriptor, in the explicit descriptor, is that we are using it only, TF-IDF, only on concepts. So that's why we have better results than TF-IDF applied to everything. We have also compared with other approaches, the one with okay, lists which are they are mentioned on the paper, and as you can see, TF-IDF to the concepts, it's a better approach. So TF-IDF is still a very good approach, only after using concepts. So for the implicit descriptor, again, as I said, the implicit descriptor is a set of keywords or a set of concepts which they do not occur explicitly on the document, but are somehow related to it. Our idea is that the implicit keywords have or must have a strong semantic proximity, again the semantic relations, have to have a strong semantic relation with the explicit keywords. So for the computation of this semantic proximity, we use these 2 things that won't be new if you saw my last presentation. So first of all, we do a correlation. Okay, it's like I said, I think everyone was here previously. So we do a correlation between an A and B, concepts A and B, and in this case for our English corpus, as you can see, Swan Pan, which is the name given to the Chinese abacus. Okay, the correlation is 100% because they only occur in one document. So the idea with the correlation is that if a pair tends to occur in the same documents, they are related. So Swan Pan, Chinese abacus occur on only one document, 100% relation. Supply demand, Microsoft Windows, okay, and then we have electricity in Mozart, which they are not related at all. For the intra-document proximity, This was a little bit previous to our work about the clusters, okay? And the clusters has another problem. The idea is that, first of all, the correlation is not sensitive to the document, okay? I'll give this an example. The correlation between the words Swanpan, the concept Swanpan and Chinese abacus, it's the same as Swanpan and Babylonic abacus because they only occur in one document. But the problem is that Swanpan is indeed a Chinese abacus. It's not a Babylonic abacus. So our idea with the intra-document proximity is this formula. I won't give it too much details, but the idea is that we have a relation between the distance of both concepts and how far they could be. So idea is this. The closer that the A and B tends to occur, okay, the more semantic related they are. It's our idea with this approach. And we give, to prevent bias towards longer documents, we divide it by the furthest distance that both could be. The farthest distance is like A being on top, or all occurrences of A being on top and all occurrences of B being on the bottom. So it's just the distance. And with this, we can somehow clarify or separate better the relation between Swanpan, Chinese abacus, and Babylon abacus. So it better understands that, or this metric better understands, if I can put it this way, that Swanpan is more of a Chinese abacus than it is a Babylon abacus. So the symmetric proximity, as I say, it's these both things, the correlation and the analysis on the document. So we do that multiplication. We do a square root to the analysis on the document because we want more weight to the information given on the whole corpus. Finally, we compute the implicit descriptor, or better, for some, I could say that was all concepts not on that document. So we have a document. We want to know its implicit descriptor. So we have the list of explicit. We have the list of keywords. We want to know what keywords or what concepts not occur in that document but could somehow describe it. So our idea is we go to each one of the other documents. In practice, we don't extract all possible keywords of all possible concepts of each document. We only extract some, okay? And we measure the semantic proximity of that concept from other document and all the explicit keywords of the document we are analyzing. How? The idea is that that concept C is the explicit descriptor of document D. If it, well, we do this sum, and we divide it by the position of the explicit descriptor. So, for instance, if we are comparing C with the first keyword, we give it the 100% of the semantic proximity. Then we will add 1/2, or yes, 1/2 of the second of the relation with the second explicit keyword, 1/3 of the relation with the third explicit keyword, so on and so forth. The idea is that the more we travel down through the list of explicit keywords, the less the relation matters to the computation of the implicit descriptor. So here are some results. Okay, so we only measure the precision. For English, Portuguese, and German, as you can see, the results are somehow similar. We don't measure recall because to measure recall, we had to see if we could find on the 2,000 other documents, if we could find a better concept to describe implicitly that document. It wouldn't be impractical, so we just have precision values. And some small examples. In this case, for the brain document, okay, the brain document doesn't talks about or better, peripheral nervous system. Although it doesn't occur on the brain document, it's somehow related to to the topic brains and things that the brain document talks about. Transverse nerves, it doesn't occur also on brain document. It's related. Okay, cerebral cortex, words like this. So this is a list of words which do not occur on brain document. This is also an example for the German immune system German document. Okay, well, I don't know if there are German people here, but you will understand English. For instance, this components. I think it's the translation. It's components of immune systems. Okay, this document talks about immune system, and the component of immune systems is an implicit keyword. It doesn't occur on the document, but I think it's related with it also as reaction of human systems. Okay, so that's what we call implicit keywords. Okay, so thank you very much. If you have questions. No questions. One question. No.
How does your work relate with name entity recognition?
Named entity recognition. How does we didn't try to do things with named entity recognition.
But
so
you can profit from those techniques.
Oh, probably we could profit from everything if we had time. The problem. Yeah.
There's tools available in the web, so you can use them as a startup.
You're talking about the explicit keywords.
Yes.
Yeah, but okay. Although the explicit keywords part is more like a bridge to the implicit keywords. We use it for the implicit keywords. Okay, we could use. Yeah, it's like a bridge. We just let's say. Our main focus on the explicit keywords part on our work is just to say that TF-IDF solves the problem. TF-IDF is a very simple thing. It solves the problem if we use it with concepts, with the concepts extracted with our extractor. So, in fact, I'm here selling two things, this work and the extractor. Say, if we apply TF-IDF to the concepts, we don't need complex things. It's a very simple thing, and the concept extractor is also a simple thing. So, the explicit keywords are just is then a bridge to the implicit keywords, which we think it's the most innovative part of this work. But in name entity recognition, it's a very explored area. It has, yeah.
Any more questions? No? So, thank you. Now we move to the last paper of this session. It's Biotext Retriever, yet another information retrieval system by Cecília Talma Gonçalves, Rui Camacho, and Eugênio Oliveira.
Microfone, esse cara não precisa. Podia segurar aqui um bocadinho. Eu posso usar aqui estas teclas, não é? Okay, good morning. So this is the PhD work of Célia Gonçalves. I'm Rui Camacho, the presenter, and in this talk I will be reporting the work, part of the work of this PhD. So the things I will be talking about is what is the real problem that we try to address with this PhD work. We actually implemented, actually it was Célia, implemented a system called Biotext Retrieval that's available on the web. I will show you the web address. And I will talk about the main part of this web tool, that is the dynamic construction of a classifier. And then I'll show some results and draw some conclusions. So the main motivation was given by a biologist from Molecular Biology Institute. And the idea is, as most often these biologists get new DNA or protein sequences, and they want to be aware of what kind of work have already been done related to those sequences. So the tool we have developed just receives as input DNA or protein sequences and outputs a set of papers from Medline that is related somehow with these sequences. So the biologist can study or be aware of what are already been done in that domain. So the main problem is, as usual, repositories like Medline and PubMed have a huge amount of documents, so extracting documents may be a pain in the neck because most of the retrieved documents may not be relevant for the work. And that's the problem we want to address. Given these sequences, fine-tune a classifier related to those sequences, and then go to Medline and filter out the relevant problems. Okay? So the main objectives are here summarized. We implemented a TextMine tool for retrieving documents from Medline, a huge repository of documents, and we construct during the query process a model using machine learning algorithms, and this model will be very suited or adequate for retrieving the relevant problems. So there's lots of tools available on the web, from either general machine learning, some dedicated to text processing. As far as we know, none of them fulfills all requirements of this task. So the architecture for this tool is based on these 6 steps. We, as input, as I said, we receive the sequences, DNA or proteomic sequences, and we get a e-value. I will explain later what this is and what's for. And then with this information, we get related sequences already stored in database like NCBI. With these related sequences in this database of NCBI, you can get papers that already been put there, and they are actually reliable. They were put there by the researchers that investigated the sequences. So this is curated data. With these papers related to similar sequences, we construct a data set, and with data set we train a classifier and go to Medline, filter out the relevant papers, and we rank them to present to the user. In the talk today, I will talk about all these steps up to step 4. So this is the first part. As usual in information retrieval, there's lots of preprocessing that we have to be done. They are more or less standard. And in this case of going from sequences to papers, we do the following. So the input sequences are given to an NCBI webpage where you can get, using BLAST, a set of similar sequences, other sequences, and associated with each of these similar sequences, we get a set of papers. Okay? Then with this, the references for those papers, we go to Medline and extract all the titles and abstract from those papers, and we pre-process them, as I will explain later. And those pre-processed papers are part of the data set, are what we call the relevant papers or the positive examples. Okay? For things to work properly, we have to collect also negative examples, get the second class, because we transform this problem into a binary class machine learning problem. So I will also tell you how we get to the negative papers to get to the full data set. But first, let's look at what we have done as processing. So it's standard procedures. We do this handling of synonyms. We have synonym dictionary, word validation, so every word that doesn't appear in the dictionary we throw away. We try to do some pruning, remove highly frequent words and infrequent words, stop word removals, and stemming as well. So to evaluate this pre-processing, we make a testing data set with mesh words from the Medline with the 4 mesh terms that are on the right side, and we took 20,000 papers from each mesh word, and so we have a 8,000 papers data set. And this data set, we use this handling synonyms with and without the handling synonyms, with and without word validation, and these levels of pruning. So there's 16 possibilities. And we run 3 machine learning algorithms like CMO from WECA, IBK from WECA as well, and J48 from WECA. And the best combination are reported at accuracy, true positive F measure. And the results we got for the pre-processing was to not use, use synonyms. So we remove synonym words and replace it for just one word. Use word validation. Don't use pruning, and use stemming and stop word removal. So this the pre-processing we do for our tool. Another thing we do is we have to generate the second class, the negative examples. So what we do is when you use a BLAST, that is the algorithm that's going to fetch similar sequences, there's a measure of similarity called E-value that determines the distance in the similarity between two sequences. And what we do is the user just establish a cutoff. So sequences that are similar with E-value less than the threshold are considered quite similar, and we take those as the positive examples. And sequences with a very high E-value are considered the negative examples. We established a gray zone to avoid confusion and to facilitate the construction of the classifier. One problem with this approach is that sometimes if you have a small number of, or a very original sequence of DNA, you might not have a lot of sequences on the database, okay? So in some cases, we got positive examples and a scarce number of negative or none of the negatives. So what we did is we, again, evaluated 3 possibilities of constructing the negative examples. If we have enough negative examples on the blue zone, we call it near misses because they are very close to the positives, okay? And if we have enough examples on that zone, we build a data set with equal number of positive and negatives, and we call it NMV approach. On the other hand, if we have a small number of negative examples on the blue zone, we use the mesh terms and go to Medline sampling the papers with the same mesh terms as the positives, okay? So we randomly sample papers from Medline with same mesh terms as the positives and complete the negative examples. If there's no negative examples at all, we just go randomly through Medline and sample a number of negative examples equal to the positives, okay? So we tested these 3 ways of generating negative examples. Again, we use different algorithms, machine learning algorithms from WECA, and if you look at the graph on the right, the best results we got is to simply random generate examples from the Medline, okay? So that's the best score in this approach. So we discard the near misses approach and the random values with common mesh terms, and we use just sample random values from Medline, okay? So this is what we do for the pre-processing, and at this point we have a data set that is useful for constructing a model that will be used to filter out papers relevant to the input sequences. Now, which machine learning algorithm should we use to construct that model, and how should we use it? We tried several possible combinations of uses of algorithms. These are the algorithms from WECA that we have used. And these are the data sets where we tested these different hypotheses. And what we have done is to either assess individual algorithms, try to assemble, use assembles of algorithms, try to partition the data different ways, and try combinations of all these previous approaches, okay? And that's what I'm going to present you, is the different alternatives and the results of this comparison. So in the first alternative, we just run individually each algorithm on the whole data set, okay, and compute the accuracy, true positives, F measure, etc. Okay, these are the results. So best performance is by J48, the ones on bold, decision tables, and BaseNet. Okay. In this first run, we try to use a different sort of algorithms, a relational algorithm, inductive logic programming algorithm called Aleph, to see if handling structure of documents would improve results. But actually, Aleph runs forever in this size of data set, so we didn't got good results with the relational learner, and we indeed the further alternatives we just discarded. The second approach, we take the all documents and run all algorithms on the all data set, and then we do use an ensemble. We using majority vote to get the classifier. Sorry, we use 3 different ensemble algorithms: ADA boost, bagging, and ensemble selection, all available in the WECA tool. Okay. In these results, almost all the results given by the ensemble algorithms are not statistically different, so you can just choose one of them. Looking at the graph on the right side, we just use ADA boost, but they are not statistically different. The third alternative you consider is to split the data and run one classifier on each subset of the data, and then make the ensemble at the end. Okay, and that's the results we got on the right side. The fourth alternative is to split the data and run all algorithms in each partition subset of the data, and then making the ensemble at the end. And one final alternative is to split the data, run all algorithms on each subset, make an ensemble for each partition of the data, and then make a final ensemble combining the previous results. The overall conclusions for all these 5 alternatives are here in this picture and table. You can see alternative 2 is the best one, although there is no significant statistical significance between alternative 1 and alternative 2. Okay, but this is as accuracy is concerned. If we do another statistics, that if you compute the position, the ranking of each alternative on the all alternatives, alternative 2 appears always in first. Okay, and sometimes equally first or not statistically different from others, but is always in first. So our suggestion is for these cases you should use alternative 2. Okay. This has been implemented, as I said, in a tool that's available on the web in that address. Sorry for the screen out. It's the contrast of colors is rather awful, difficult to see. But this is the entrance of the tool where the biologist can put the sequences in the upper box in FASTA format, specify the e-value, the threshold for similarity, and then the model is constructed by this the procedure I just told you, and a set of documents are shown to the user, ranked by ranking function, and then clicking on each document, you can see what's the document and the title and abstract. Okay, so this work is we have fulfilled the requirements from the biologist, just going from input DNA sequences to a set of related papers. The tool is available on the web. This is future work. We have to put the biologists using it and give us some feedback. Okay, so far it just gave us the problem and some clues for the development, and that's about it. Thank you very much.
Classification for this kind of problem, or Instead
class.
of, for example, one class classification instead of binary classification. I mean, you have just positive.
How do you go about with one class?
I mean, you just have the positive cases, not negative cases.
Yes, but generalizing from one class, you just get a useless rule usually. Because you need a contrast class. Well, ILP, for example, I have some approaches where I can build models from just positive examples. But in propositional learning, like building a decision trees, you just say it's class 1 and gets 100% of accuracy. So I don't see how you can go.
I mean, novelty detection, for example.
Sorry?
It's a different field. In VK, for instance, there is no algorithm for one class classification.
Mm-hmm.
I mean, but when you don't have access to negative, because it's in most of the times you don't have access to negative cases. So you have only positive cases. So you want to detect the papers that are coming from out of the distribution. You know, you have you say that this paper is out of the paper distribution of the papers that I have. So it's only one class classification.
I think with propositional learners, that's a very hard question.
It's not implemented in that
yeah, but
case.
if you use ILP, inductive logic programming, there's an approach by Steve Muggleton that you can have only positive examples.
Mm-hmm.
And the idea is based on compression. When you generalize, you get shorter descriptions. So somehow you compress the description. And learning from positive only is based on this compression idea. And if you run Aleph with that possibility, it should work. But it's the only case, I think, where you have algorithms for positive only examples.
Yeah. But you did something?
No.
Okay.
I think it was easier to get these negatives
Mm-hmm.
and get because the problem with ILP is very slow. You can add lots of background knowledge, but as you add background knowledge, this hypothesis space just exponentially expands, and you wait for a model for days, and you are not willing, in the online tool, you're not willing to do that. So we have to stick with propositional algorithms, and for that we need the second class.
Okay, thank you very much.
Any more questions?
Yes? This one? No. Sorry. These are the alternatives.
You say it is the best one.
Yes. This is the ranking. So it gets always first. The lower, the better. Okay? Because the previous one was accuracy. The highest, the better. Okay?
Thank you.
Well,
So, are there any more questions?
so let's go for lunch.
Yeah. So we end the first session. Thank you, and nice lunch. The second session starts at 2 p.m. here in the same room.